All right, we'll finish up today with a brief discussion on mobile phase effects in gas chromatography. So we've said that we call the mobile phase the carrier gas. We do this because that's all it does. That's the function of the mobile phase in gas chromatography. All it does is carries the analyte toward the detector. That is to say, it effectively has it has no effective solvating power. It is not dissolving the stationary phase the way that, the analyte. It's not dissolving the analyte the way that solutions dissolve, um, molecules into them. There is no uh, competition. There's no mobile phase, stationary phase competition as there is in liquid chromatography. Um, so it might seem like it really doesn't matter what mobile phase you use, right? Your carrier gas could be literally anything you have a cylinder on hand of, right? You got an old cylinder of argon, just shove that thing on your GC. Actually, it does make a difference. So selection of the mobile phase still matters. For a couple of reasons. The first is it has to be compatible with your detector. We're going to see that I'll give you an example of this. We're going to see that hydrogen gas is a common mobile phase, probably not a great solution if you're going to do something like atmospheric pressure ionization, atmospheric pressure chemical ionization in front of in front of a mass spec, because that's a spark and you pump a bunch of hydrogen, flammable hydrogen gas on a spark, and stuff won't be very pretty. So it's, with the gas selection still needs to consider what's going to happen to this gas after it leaves the column. But actually, there's a good chromatographic reason why it still matters, and that is to say that different gases have different viscosities, right? Here's our eta for viscosity. Different gases have different viscosities, and that's going to give us one very, very important difference, and that is the diffusion coefficient, capital D. I'm going to say sub-analyte. The diffusion coefficient of our analyte in our mobile phase gas, our carrier gas, is going to make a big difference on the separation. So let's look at three really common, before we understand how that works, let's look at three common choices for carrier gas. So three common carrier gases are nitrogen, helium, and hydrogen gas. And if we compare these in terms of the diffusion coefficient of our analyte in each of these, typically this is what you would see as a trend. You would see that the diffusion of an analyte in nitrogen gas is quite a lot less than the diffusion of an analyte in helium gas. Hopefully this makes a little bit of sense. If you think about the mass of these gases, right, that's much heavier than that. And so if you have a particle that's trying to kind of by Brownian motion move its way through that gas, it's frequently crashing into much heavier molecules. They're going to slow it down. So it's going to diffuse a lot more slowly than it does in a lighter gas. Turns out that this is less, or for some analytes, maybe close to approximately the diffusion of those analytes that they'd experience in hydrogen gas. Okay, so I said this is going to make a difference in terms of our separation. Let's consider how this affects Van Deemter. Not the guy, but his equation. I'm sure he's totally fine with all of it. Let's see how this affects the Van Deemter equation. Specifically, let's look at the Van Deemter factors, B and C. Make a couple of plots here. So let's start by just plotting the Van Deemter B term. So the Van Deemter plot is height equivalent to a theoretical plate versus the average velocity or the average volumetric flow rate. And we're looking just at the B term. I'll remind you, if you remember the Van Deemter equation, that the height is proportional to the B term over that average velocity, and lower heights are better, right? Lower heights give us more numbers of theoretical plates. So let's just draw something with that shape, with the shape of 1 over V. It would look like that. So here's what I'm going to do. I'm going to arbitrarily tell you that that is the curve for helium. Okay, let's consider what's happening here. It's basically telling us the faster we go, the better. That's because the B term is about longitudinal diffusion. How does a plug of analyte spread over time as it's moving down the column? And so you have some rate of diffusion in this helium, and the slower you go, the longer it's going to take to get to the end of the column, the more it's going to diffuse longitudinally. So let's think about what a change in diffusion coefficient means. It means that that band broadening is happening slower as the diffusion coefficient gets lower. And so if we take a gas like nitrogen that has a lower diffusion coefficient for our analyte, it's going to mean, I'm going to draw this going backwards just because it's easier for a right-handed person. It's going to mean actually we can get to lower velocities. We can take a little bit longer to get through that column and maintain slightly lower band broadening, slightly lower values for H at those lower velocities because diffusion's happening more slowly, right? So let's call that our value for nitrogen. And in terms of the B term, we're going to say the nitrogen gas wins. It's the better choice, okay? Now let's consider the C term. And I'll remind you that our height is proportional to C times our average velocity. So there's height, here's our average velocity. This is a nice linear relationship, so there's a line. I'm going to tell you this line belongs to helium. So how does diffusion affect this? Well, this is all about the resistance to mass transfer. It's all about the, I can see that's a little bit faint. Let me darken this in. It's all about how much time it takes for an analyte to find its way into and then back out of a stationary phase. And the faster something diffuses, the less time it takes, the better, right? So when an analyte has slightly faster diffusion in helium, it has slightly lower resistance to mass transfer. So if we were to plot this for nitrogen, it would have a higher slope like this. That is to say that the faster you go, the worse, relatively speaking, the H gets for nitrogen as compared to helium. So in this particular half of the equation, we can say that helium wins. Right? Helium is the better solution because its band broadening grows at a slower rate than the band broadening due to resistance to mass transfer would grow for a mobile phase of nitrogen, or carrier gas of nitrogen. Let's consider the whole Van Deemter curve then. So if we add these things together, here's roughly what we'd see, and this is just kind of relative relationship. So here's N2, and what we would find for the lighter gases is that they may not quite hit the same optimal H. So this may actually be a little bit lower than that. Let's call this helium. And hydrogen has a very similar, it's going to do something like that. So they may not hit the exact same, it's going to be similar, but they're not going to hit the exact same optimal H value. But the trick here is that you hit that optimal H. So H optimal comes, we'll say, on the order of like 2 times higher. Sorry, we haven't labeled these axes. That's V, that's H, 2 times higher of our average flow rate. If you remember back to when we first talked about Van Deemter, we said we never work on this side of the optimal, but we very often work on this side of the optimal because there's only so much resolution you need, right? Once your baseline resolved, you're pretty good, and faster analyses are better. And so coming at twice um, the volumetric flow rate of nitrogen means faster, probably 2 times faster analysis times. So last thing we'll say, and then we'll call it a day. You guys are familiar with the good old Van Deemter equation. Let me remind you. That is that H is equal to some term A, which is constant. That's eddy diffusion, plus this longitudinal diffusion term we just talked about, which is proportional to B over our average velocity, plus that C term we talked about times our average velocity. And the point I want to remind you of, we've touched on this briefly before, is that gas chromatography is done in open tubular columns, right? So there is no A term. So for open tubular GC, there's no A term, and that reduces the Van Deemter equation to something we call the Golay equation. That's supposed to be 2 words, Golay equation, which is pretty predictably B over V plus C times V, no A term. So this is one of the reasons why, if GC is going to work for you, you should use it, because you're going to get much better plate counts, at least in part due to the lack of that A term.